These are questions 11 to 20 of our multiple choice. These ones are slightly simpler, actually, and require a little bit more remembering of the basic concepts in terms of momentum, impulse, and Newton's laws. We've got an inelastic collision occurring between the two bodies in the absence of external forces. What must be true about the total momentum and the total kinetic energy? Well, in this case, we know that if there are no external forces, the momentum is always conserved. The collision is inelastic, which means the kinetic energy is not conserved, and so therefore only momentum is conserved. This is going to be a recurring theme through these questions. All right, let's have a look at this. This is a nice one. Ball of M strikes a vertical wall at an angle. What is the change in the magnitude of the momentum of the ball? In this case, what I'd like you to do is think about breaking up into components. If we see here, we've got two directions, x and y. Our initial momentum in the x direction, we're moving to the right with mv cos theta. We're just using our components here. And we're moving down, mv sine theta. Now you notice when we bounce off the wall, we actually find that we're still moving down. In that case, our final momentum in the y direction is still mv sine theta. We've moved off at the same angle. It's essentially a reflection problem, and so therefore the magnitude of our momentum in the vertical direction has not changed. Okay, now if we look at the horizontal momentum, you should be able to see that we've changed our direction. In fact, we've kind of flipped it 180 degrees. We're now moving backwards where we were moving forwards, and so therefore our final momentum is minus mv cos theta. If we find the change, then it's just the final, take away the initial, and we've got minus 2mv cos theta in the x direction, and therefore 0 in the y direction, because minus of the same number gives us 0. In this case, we end up with 2mv cos theta. Two objects, M1 and M2, approach each other. The objects collide and stick together. Total change of linear momentum. This is a trick question. Assuming we have no external forces, the momentum is always conserved. So therefore the total change is going to be 0. Read these questions carefully when you see them. Okay, make sure that you are thinking about the fact that the total momentum is always conserved. In, for example, one of the answers here, let's have a look. Our total momentum at the beginning is m1 v1 minus m2 v2, which could be, for example, this one here. All right, that's actually the difference in the momentum between the two. It is not the change in the momentum. The change is always 0. No external forces, inelastic collision. Okay, well, when we're thinking about linear momentum, our linear momentum must be conserved. Okay, linear momentum must be conserved. It's not something which is conditional, it is a requirement. Okay, so our answers here are either B and D. Kinetic energy is not conserved in an elastic collision, and so therefore our answer here is D. We're repeating a similar question here from the previous ones. Very nice question, this one. Okay, we've got an object of mass m1 and kinetic energy e1, and mass m2 and kinetic energy e2. The objects have the same momentum, but we want to know the ratio. Now here you can use two equations. One of them is half mv squared, or you can use p squared over 2m. Now these are exactly the same equation. They're just calculated simply by substituting p equal to mv here. If you notice here, I've got mv squared. So if I multiply and divide by m on the top and bottom, I can rearrange, I can get p squared over 2m. I would go for the second one here, because then we've got a nice little bit of maths to play with. E1 over E2 is just the ratio of the two kinetic energies. P1 squared over 2m1 divided by P2 squared over 2m2, and then you flip it because we are dividing by that quantity there. So our P1 and P2 are on the top and bottom here. We are told here in the question that they have the same momentum. I'm going to call that P. Well, those P squareds can cancel each other, as can the 2's, and we're left with M2 over M1, which is why the answer there is C. Very tricky question, this one. Requires a lot of thinking about the maths. Have a second to look at the working there and follow through and see that it makes sense to you. Collision between two bodies, Newton's third law. Well, Newton's third law is universal, okay? It means it always applies, okay? In that case, it may be that we don't conserve kinetic energy or momentum, etc. However, we always have a third law, okay? Always applying means universal, and so therefore you can always use it to understand what's going on in a collision between two bodies. Whether they're external forces, etc., goes into the maths, however, the law will always apply. Same with Newton's second law and first law. Net force on a body is F. Okay, well, we're told F net is the rate of change of momentum. We multiply that by delta T to get delta P. And we define I as the product of F and T here. And so therefore I, the impulse, is the change in momentum of the body. This is always the case. If you can calculate the change in momentum simply by calculating the impulse of the body, i.e. the force times the time. In an elastic collision, we've had this before. External forces, momentum always conserved. Inelastic collision, therefore kinetic energy is not conserved. Momentum of an object changed by delta P in time delta T. What is the impulse? Again, the impulse is the product of force and time. That is equal to the change in momentum, and so therefore the impulse is the change in momentum here. Last one, I like this one a lot, okay? Egg dropped on the floor, likely to break. When it's wrapped in a cloth, it's less likely to break. This is because, well, we think about it here, when we're trying to break an egg, we're trying to use force. Large force will break the egg, low force may not. Well, to see how this works, we need to use our force is equal to delta P over delta T. Okay, delta P is simply the change in the momentum. We assume that the change in momentum is constant here, i.e. we're going to simply bring the egg to rest, and we assume it's dropped from a consistent height. Okay. If we have a softer cloth, we're going to increase the collision time. We'll take more time to do the collision, and so therefore reduce F. Let's see how that works. We've got a constant value here on our right-hand side, that's delta P. If delta T goes up, then F must go down, thus reducing the chance of the collision breaking the egg by reducing the value of the force.